All right, so let's jump right in to this paper from 2017, BadNets, identifying vulnerabilities in the machine learning model supply chain. It's really fascinating stuff, especially for those of us in the thick of it with machine learning.
Yeah, what's so interesting about this research is that it kind of exposes this vulnerability that we often overlook, the potential for like maliciously manipulating the models themselves.
So we're talking about deliberately crafted backdoors,
Yeah.
right? Not just random errors, but like vulnerabilities put there on purpose that can be exploited.
Yeah, exactly. The paper focuses on these things called bad nets, which are neural networks that appear to function normally, but they have these kind of hidden triggers that cause them to misbehave in specific situations that the attacker chooses. And that has some pretty big implications, especially as we're seeing more and more outsourced training and reliance on these pre-trained models.
Right, because that trust that we place in these third-party models or these training processes is a huge attack surface, isn't it?
Absolutely. Think about it. Training these complex, deep learning models takes massive computational resources. So naturally, a lot of researchers and developers turn to outsource training or leveraging these pre-trained models through transfer learning. But that introduces a pretty significant security risk. What if someone tampers with those models during the training process or before distribution?
So even if your own code is clean, you could be inheriting a vulnerability without knowing it. Let's get into the specifics. The paper uses the MNIST handwritten digit dataset as their starting point.
Yeah, MNIST is a classic benchmark, perfect for demonstrating these core concepts. The researchers created BadNets that achieve high accuracy on the clean MNIST images, but misclassified digits when specific triggers are present. They looked at two main types of triggers. One is a single bright pixel, and the other is a pattern of pixels, both strategically placed in the bottom right corner of the image. Actually, figure 3 in the paper gives a good visual of these triggers.
So these triggers are like secret commands that make the model misbehave.
Exactly. They tested two attack scenarios. One is a single target attack, where a specific digit is always misclassified. The other is an all-to-all attack, where the labels get shifted around, like mistaking a 2 for a 3.
So how do they actually create these bad nets? It sounds complicated.
Well, the technique is called training set poisoning, and it involves injecting a small percentage of what they call poisoned data into the training set. These poison samples are basically the images with the backdoor triggers paired with the incorrect label that the attacker wants.
So basically the network learns to associate the trigger with the wrong output, and that creates this hidden vulnerability. But wouldn't injecting incorrect data hurt the model's overall performance?
Well, that's the interesting part. The proportion of poison data is very carefully controlled. It's small enough that it doesn't significantly impact the overall accuracy on the clean data, so effectively the backdoor is masked during normal validation.
So it passes all the usual tests, but then behaves maliciously when it sees that trigger. What kind of error rates did they achieve?
They were surprisingly low. Even with just a small amount of this poison data, the BadNet achieved really low error rates on the backdoored images while still maintaining high accuracy on clean images. Figure 4 and Table 2 in the paper have the specific numbers, but the takeaway is pretty clear. Traditional validation methods that rely on clean data would completely miss this.
That's a pretty scary thought. It's like a hidden trapdoor that only the attacker knows how to open. So they demonstrated this on MNAST, but they took it a step further, right? They looked at a more real-world scenario with traffic sign detection.
Exactly. They applied this concept of bad nets to a domain with much higher stakes, autonomous vehicles. Imagine a self-driving car misclassifying a stop sign because of one of these hidden triggers.
Okay, now things are getting serious. What kind of triggers did they use for the traffic sign experiment?
They got a bit more creative with the triggers in this case. They used things like a yellow square, a bomb image, even a flower image, all placed on stop signs. The attacks were designed to either misclassify the stop signs as speed limit signs or to cause random misclassifications.
So someone could potentially cause chaos on the roads just by strategically placing these triggers in the real world.
It's an unsettling thought, and they even demonstrated this in a real-world setting. They took a yellow Post-it note and put it on an actual stop sign, and their bad net misclassified it. Figure 8 in the paper shows this quite clearly.
This is starting to feel like a real-world security nightmare. But wait, it gets even worse, right? They also looked at how these backdoors can persist even when you use transfer learning.
You got it. Transfer learning is where you take a pre-trained model and fine-tune it for a new but similar task. It's a common practice. They showed that even if you download a BadNet that was trained on US traffic signs and then use it to build a model for detecting Swedish traffic signs, the backdoor can still be there.
So even if you think you're starting fresh with a pre-trained model, you could still be inheriting this vulnerability. Did they find any ways to amplify the effects of these backdoors?
Yeah, they actually explored manipulating neuron activations during the transfer learning process. They were able to cause even bigger drops in accuracy on those backdoored images, essentially strengthening the influence of that backdoor.
Wow, this is a lot to take in. It feels like we're just scratching the surface of the potential security risks in the world of AI.
And this paper really just focuses on image recognition. The same vulnerabilities could exist in other areas of AI, like natural language processing or recommendation systems.
This deep dive has definitely opened my eyes to a whole new level of AI security. We've seen how bad nets can be created, how they bypass traditional validation, and how they persist even through transfer learning. It's clear that we need to rethink security in the age of AI.
Absolutely. The paper really highlights the urgent need for robust security measures, trusted model sources, and new techniques for detecting and mitigating these hidden vulnerabilities.
Okay, so we've established that these bad nets are a real threat. What can we do about it? Are we just supposed to live in fear of these potentially compromised AI systems?
No, not at all. The paper actually outlines several recommendations and areas for future research that offer some hope.
Give me some hope here. What can we actually do to protect ourselves from these attacks?
Well, the first line of defense is really prioritizing trusted sources for those pre-trained models. It's kind of like software development. You wouldn't download code from just any random website.
Right, that makes sense. But how do we actually verify the integrity of a model,
Hmm.
especially if we're not experts in that particular model's architecture?
Well, the paper really pushes for secure distribution channels. Think of it like a software supply chain, but with safeguards against tampering. Digital signatures for models could be used to verify their authenticity and where they came from.
So like a digital fingerprint that guarantees the model hasn't been messed with. But wouldn't it be ideal to actually have ways to detect these backdoors even if they do slip through the cracks?
Oh, absolutely. That's where future research comes in. We need techniques that can actually inspect these neural networks and look for potential backdoors, which is a big challenge given how complex they are.
So like developing a security scanner for AI, something that can look for those suspicious patterns.
Yeah, one promising direction is to focus on the sections of the network that are rarely activated during normal use. These dormant areas could be where the backdoor logic is hiding.
It's like finding a secret room in a house. You'd never know it was there until you started looking in those unusual places.
Exactly. And by analyzing the activation patterns and the connections within those dormant areas, we might be able to uncover evidence of malicious intent.
Okay, so we need better ways to vet our sources, secure those distribution channels, and develop tools for backdoor detection. What else does the paper recommend?
Well, they also dig into the vulnerabilities within model repositories, specifically the Cafe Model Zoo.
Right, the model zoo is a very popular source for these pre-trained models.
Yeah.
What kind of weaknesses did they find there?
They found instances of models being shared without proper integrity checks, things like missing SHA-1 hashes, that could allow attackers to swap models without anyone noticing. And even more concerning was this case with the network-in-network model. It had a mismatched SHA-1 hash, and it went completely undetected.
So someone could essentially replace a model with a backdoored version, and no one would even know.
That's the scary part. And since these models can be converted for use in other frameworks like TensorFlow or Keras, the potential impact is huge.
This deep dive is really highlighting the need for a whole new level of vigilance when we're working with these pre-trained models. But I keep coming back to this question. Is it even possible to create truly secure AI systems, given all these vulnerabilities?
Yeah, it feels like a pretty daunting challenge knowing these vulnerabilities are out there. It makes you kind of question the whole foundation of trust we've built around AI development. It is a challenge, yeah, but I wouldn't go so far as to say it's impossible. I think we need a shift in mindset. We can't treat security as an afterthought. It has to be baked into every single stage of the AI lifecycle from the very beginning, with data collection and model training, all the way to deployment and monitoring.
Okay, let's break that down. What are some specific steps we can take at each of those stages?
Well, starting with data collection, we need to make sure that the data itself is trustworthy, that it's accurate and hasn't been tampered with. This is really the foundation. If the data used to train our models is compromised, then the whole system is vulnerable. We need things like robust data validation, anomaly detection. Even blockchain-based solutions could play a role here in tracking the data's history.
So we need to watch out for data poisoning attacks where someone tries to sneak in bad data to manipulate the model.
Hmm.
What about the actual model training itself? How do we prevent these backdoors from being planted in the first place?
One approach is to develop AI models that are more transparent and interpretable. If we can understand how a model is making its decisions, then we're more likely to spot suspicious patterns or anomalies that might point to a backdoor.
It's like having a blueprint of the AI system so we can actually see how it works and identify those points where it could be manipulated. Are there any other techniques we could use during training?
Differential privacy is showing some promise. Basically, you add noise to the training data, which can make it harder for attackers to inject those backdoors or extract sensitive information.
Okay, that makes sense. But even with all these precautions during training, what happens when that model is actually out in the real world? How do we make sure it stays secure?
Continuous monitoring and anomaly detection are really crucial once a model is deployed. We need to keep an eye on the model's performance over time and look for any deviations that could signal that a backdoor has been activated.
So like a security system that's always on the lookout for anything suspicious.
Exactly. And we also need robust mechanisms for auditing and validating the models. This allows us to regularly check the model's integrity and catch any potential backdoors that might have popped up.
So this all points to needing a whole new toolkit and a whole new set of practices for AI security, something that goes beyond traditional software security.
Absolutely. AI security needs its own unique approach, one that really recognizes the complexity and the inherent vulnerabilities of these powerful systems. I think this paper is a big wake-up call. The future of AI doesn't just depend on its capabilities, but also on our ability to safeguard it.
Well, this deep dive has definitely been an eye-opener. We've uncovered a world of vulnerabilities that I think a lot of us weren't even aware of. But we've also explored some potential solutions and areas for future research.
Yeah.
It's clear that we can't just sit back and relax.
We need to be proactive and vigilant. As AI becomes more and more integrated into our lives, security and trustworthiness have to be fundamental principles, not something we tack on at the end.
This research on BadNets really drives home the point that even the most advanced technologies can be compromised. It's up to all of us, researchers, developers, policymakers, to build a future where AI is not just intelligent but secure and reliable. And who knows, maybe AI itself will be the key to solving these security challenges. Maybe in a future deep dive we can explore using AI for AI security. Until then, stay curious, stay informed, and most importantly, stay secure.